Hi, in this video I will explain the idea of cents used in the context of musical intervals. We will start by recalling a familiar experience that all of us have had. We went to a birthday party and it was time for people to sing the birthday song. Let's say there are two guests, Tanya and Ram, and Tanya starts singing the birthday tune like this. Happy birthday to you. Concurrently, Ram starts singing the same birthday tune, except he sings it like this. Happy birthday to you. Concurrently, a third guest starts off in another register. Net result is complete cacophony. Although each one of these people are good singers and they were intrinsically singing the correct tune. So what went wrong? So this is from this experience we will segue to the idea of sense and so on. So clearly what happened in each case was they were all singing the same tune, but they all started at the wrong place, right? So if they all started at the correct place, it would have been they would have all been right. But it's not just about starting at the correct place, it's not about the starting frequency. There is a deeper idea related to that called the tonic frequency. For example, if this was going on in the background and somebody had to sing a familiar Carnatic song, say Vatapi or something, automatically you will only go Vatapi Ganapatim Bhajeham Vatapi Ganapatim. Nobody is ever going to sing because this is the starting frequency. Vatapi Ganapatim Bhajeham. So clearly the idea of tonic transcends the idea of a starting frequency. So if they all had the same tonic, then they would have been in sync. So let's see, clearly one of the fundamental properties of all musical notes is frequency. So I was secretly recording their singing and I measured the frequency of each of these notes in Tanya's singing as well as Ram's singing. And here's what I have. So there are 5 phrases. Happy birthday to you. See, happy is it's sung staccato in 2 notes in the same time unit. So the rest of them, the notes are all legato notes. Happy birthday to you. So these are Tanya's frequencies and these are Ram's frequencies. So they're all singing the same tune. There is some relationship between the frequency that we need to find out. So the first thing I did was try to subtract the frequencies. Like 784 minus 698 is 86. 698 minus 784 is minus 86. And so that's what the adjacent differences are. And here too. And looking at these adjacent frequency differences, there is no pattern that springs out that links up these two tunes. So I tried another tack. I divided the frequencies of these adjacent of the adjacent notes. So 784 divided by 698 is 1.12. 698 divided by 784 is 0.89 and so on. And I did the same for Ram's frequencies. And voila, you can see that the adjacent ratios are identical even though they're singing in completely different regions of the sonic space. So clearly the tunes are related to each other by relative frequencies or some multiplication factor, the frequency ratios of successive frequencies and so on. So we found out the underlying principle that makes music work, which is relative frequency and relative frequency ratios and so on. So every step that you take, musical step up or step down that you take, is some multiplicative factor of your existing frequency. So multiplication and division is intrinsically hard. I mean, if you recall the time like when you were in middle school and somebody told you that you were about 1.12 times as tall as your brother, that would have made no sense. You needed to know whether you were 10 centimeters taller or shorter than your brother and so on. That is a more relatable idea. So linear steps are much more relatable than ratios. Fortunately in music, we do have such a measure that can convert these ratios into linear steps, and that is called the sense calculation. So without telling you anything about the underlying math yet, I'll give you the sense formula. If you have two frequencies, say 784 or 698, any two frequencies, F1 and F2, these are two frequencies. Now if you want to know how many cents lie between those two frequencies, you use the formula cents equals 1200 times logarithm to the base 2 of F2 by F1. Don't get daunted by logarithms, they're really cute and simple and beautiful. So logarithm to the base 2 is one thing. So each one of these has a deeper mathematical explanation. Hopefully I will be able to tell you that. So once you do this calculation, for example, for the notes 784 and 698, when I do this calculation, cents, if I do 1200 times logarithm to the base 2 of 784 divided by 698, we get this wonderful number like 200. I mean, if you do the actual calculation, you will get a little more or less than 200 because I have approximated these frequencies that I measured. If I get the precise frequency, you will get with the decimal places, you will get exactly 200. So I have used those exact numbers. So the cents that differ between these two. Now look at how beautifully this whole as a tune progresses. You start with happy, you go up 200 cents to birth, you come down to 200 cents to day, you go up 500 cents to 2, and you come down 100 cents to you. So the same thing is true for here. You can do the calculation here. So 698 by 622, if I change this to, I'll get the same 200. 698 by 622 is again 200 cents. So you see the cents, so what we've done is told you about the cents. But let's now go to the deeper idea behind cents. Now, as we all know, an octave is a special type of interval. So if you have a sound of frequency 1, I used 1 because it's easy to use. It can be anything 698, 784. Its octave is 2. And they belong to what is known as the same pitch class. So all octaves are the same pitch class. For example, if I sing is the same pitch class as, this is part of the universal human experience. So an octave is divided, the second idea that I need to introduce is the idea of a universal chromatic scale of dividing up the octave into 12 equal notes, 12 notes of equal temperament. I have a keyboard here. So that's 12 notes, and they're all equally spaced between each other. What is that space is the question. So we need to multiply 1. We start with 1, and in 12 steps we need to get to 2. So I multiply 1 by x, another x, another x, another x, and so on 12 times, and I get to 2. When we do 12 times, it is 1 into x to the power of 12 equals 2. That implies that x equals 2 to the power of 1 by 12. If you do the math calculation in a calculator, what is 2 to the power of 1 by 12? You will get something like 1.06. So this is the chromatic ratio interval. Now the chromatic ratio again is as useful or useless as 1.12 and so on. So we need to convert that into cents, which is easy, which is 1200 log 2 of 1.06, which we get to be the grand number of 100. That's a cent. That's 100 cents. So that means the difference in cents between successive notes on a chromatic scale is 100 cents. So the cents are very useful also in specifying errors in any frequency. Suppose I sang that happy birthday like this. Something wrong with that second note, right? Happy birthday to you. It's a little flat. Now, how much off was I? Somebody can say about you were about 0.9134. That makes no sense. It's just like saying my brother is 1.12 times as tall as I am. So what better can we do? We can say you were 20 cents down, 20 cents flat, or 25 cents sharp, 5 cents off. So cent is a really lovely measure to divvy up an entire semitone. They call it the semitone, right? By 100 divisions. So what does that tell you? In octave you have 12 notes. So how many cents do you have from any note to its octave? If you have 100 per semitone, in 12 semitones you have 1200. So that's the idea of the whole calculation, 1200 log of, they are all tied together like that. So that way you have if you look at the octave from any octave from sa to sa, you have 12 steps. And each of these 12 steps is divided into 100 divisions. And you can be a little off, little sharp, little flat. So these divisions are applicable across musical tuning systems, everything. I mean, it's the linchpin of any kind of tuning I adopt. For example, I adopt something called just intonation, and say the major third. This now that we know about cents, we know how far this is from this. So how many steps did we go? We went 4 chromatic steps. That means it's 400 cents off, right? But my Gandharam will be a little flatter than that. So that's a flatter Gandharam than this chromatic Gandharam. It won't be very nice in Indian classical context. Anyway, that's just an aside. The point is, I can tell very clearly that my Gandharam is flatter than the standard keyboard Gandharam by about 16 cents. Instead of 400 cents, I play my Gandharam at around 384 cents. So that's the beauty of cents. So I think we should stop here. We will continue this with any other insights in future videos. Thank you.